All right, let's jump right into this explainer and demystify the magic of digital communication. Because let's be real, every time you stream a video, send a text, or load a web page, it feels like invisible magic, doesn't it? Well, today we're pulling back the curtain. We're going to explore the actual physical hardware and the precise rules, the protocols, that literally make the internet work.
When we casually throw around terms like the cloud or the web, it sounds completely abstract, like it's just floating in the air. But the grand blueprint of it all proves that the internet is actually a highly structured physical grid. We're talking copper wires, fiber optics, silicon, and very specific rules for how traffic moves around.
We're going to take a zoom-out approach for this. We'll start small, looking at device identities and hardware. Then we'll cover the anatomy of data packets, how local network traffic is directed, the different connection types, scaling all the way up to the cloud, and finally, how this entire network ecosystem fits together.
Okay, Part 1. Device identities and hardware. Let's look at the foundational hardware inside your device and how it introduces itself to the grid.
So, to get onto the network in the first place, your phone or laptop needs a network interface card, or NIC. Built right into that card is a unique identifier. Think of the real-world postal system for a second. Your device's MAC address is kind of like a permanent social security number. It's hard-coded right at the factory. The IP address, on the other hand, that's just a temporary home mailing address assigned dynamically by your internet provider whenever you connect.
Understanding this difference is absolutely crucial. You've got your permanent hardware identity and your temporary network identity. That MAC address is a 48-bit physical identity that literally never changes. So if you take your laptop to a coffee shop, your MAC address comes with you, exactly the same. But the coffee shop's router, it gives you a brand new, temporary IP address to use while you're sipping your latte.
For the longest time, IP addresses used a system called IPv4. But thanks to everyone having a smartphone, a tablet, and a smart TV, we actually ran out of addresses. Seriously, the whole world hit capacity. We desperately needed a fix, which brings us to a massive, game-changing number, 128.
Because of that address crisis, engineers created IPv6. It's a 128-bit alphanumeric system, and the scale of it is just mind-boggling. To put it in perspective, it provides enough unique addresses for every single future device on the planet. Everything gets a permanent home on the internet, and we will never run out again.
Part 2. Anatomy of data packets. Now that we know how our devices get their addresses, let's zoom in on the actual letters we send through this digital postal system. Whether you're sending a quick email or streaming a 4K movie, that data payload never, ever travels whole. Instead, it gets shattered into thousands of tiny chunks called packets. Each one of those chunks is placed inside its own little digital envelope before being sent out onto the wire. So what's actually written on the outside of that envelope? That's the packet header. It stamps the sender IP so the network knows exactly where it came from, the receiver IP for where it's headed, the total packet size, and this is key, a sequence number. Since your file was shattered into 1,000 pieces, that sequence number is the only way the receiving computer knows how to put the puzzle back together in the right order.
Part 3. Directing local network traffic. We've got our addresses, we've got our packets. Let's look at how these digital envelopes are actually sorted in a local space.
When you connect devices locally, you need a traffic hop. The old way of doing things used a basic hub. Think of a hub like a terrible mailroom attendant who insecurely shouts your private data to every single person in the building, completely wasting bandwidth. But an intelligent switch? That uses a MAC lookup table to figure out exactly who the packet is for, and it quietly delivers it only to the intended device. Just to summarize our hardware toolkit real quick, local mailrooms, like switches and bridges, rely on MAC addresses to navigate around a single local network. But international post offices, which are your routers, use IP addresses to connect entirely different networks together, like linking your cozy home network to the massive, wild internet.
Part 4. Connectors and connection types. Let's talk about the actual physical and invisible roads that these packets travel on.
Now sure, wired connections give you the absolute fastest speeds and top-tier security, but we love mobility. When we look at wireless communication, Wi-Fi runs your home network over longer distances, up to about 100 meters with high speeds and active WPA encryption. Bluetooth is totally different. It's a personal area network, or PAN, designed for lower speeds and devices sitting right next to each other, usually within about 30 meters. To give you a visual on those distinct use cases, Bluetooth connects things like your phone and a smartwatch using spread spectrum frequency hopping.
That basically means it's constantly changing frequencies to dodge interference. Meanwhile, a Wi-Fi router acts as an access point, powering multiple laptops across your whole house with active encryption. Part 5. Scaling to the cloud. Let's see how all this local infrastructure we just talked about scales up to wrap around the entire globe. Your house, your school, or your office. Those operate as confined local area networks, LANs. But the second your data leaves your local router, boom, it shoots out into a massive wide area network, or WAN. A WAN can span across entire countries and continents. In fact, the internet itself is quite literally just the ultimate globally connected WAN.
Ultimately, a lot of our packets traveling across that global WAN end up in the cloud. And the cloud is really just a fancy term for remote servers hosting data so you don't have to clutter up your own hard drive. You've got public cloud servers for vast, easy accessibility, private clouds locked tight behind company firewalls for maximum security, or a hybrid cloud that strategically mixes a bit of both.
Part 6. The complete network ecosystem. Okay, it's time to put the whole puzzle together into one continuous flow.
Seriously, look at the device you're watching this on right now. Think about the incredible sequence happening behind the glass. Every single time you send a text or load a page, your data embarks on this exact journey across the ecosystem, moving seamlessly from your hardware to a local switch, to a router, and out to the cloud.
Let's trace it step by step. 1. Your hardware stamps the origin with its permanent MAC address. 2. The local switch reads that and transports the packet to the edge of your network. 3. The gateway router applies a dynamic IP address and checks its routing table for the fastest path. 4. The packet navigates the vast expanse of the internet WAN. And finally, 5. The packet arrives and uses its sequence numbers to rebuild itself at the remote cloud server.
Now, this global system is an absolute engineering marvel, but there's a serious trade-off here. It offers amazing rewards, like universal access and automatic data redundancy, which just means your files are mirrored across multiple servers so they don't get lost. But it also introduces major risks. We're talking potential security breaches by hackers or even total data loss if a third-party hosting company completely fails.
Which leaves us with one final crucial thought to ponder about the ultimate cost of our digital convenience. You literally have the entire world at your fingertips, but to get it, you surrender physical control of your information to servers you will never actually see. So, when you send those digital envelopes out into the vast network, is your data ever truly safe? Thanks for joining me on this explainer, and keep questioning the technology you use every single day.